we're going to work through problem 7.45 of elementary principles of chemical processes. So in this process, we have air at 38 degrees C and 97% relative humidity is cooled at 14 degrees C and then fed to a plant at a rate of 510 meters cubed per minute. So we're asked to calculate the rate at which water condenses and calculate the cooling rate in tons. And it gives a unit of cooling to be, or 1 ton of cooling to be 12,000 BTU per hour. So I've already drawn and set up this process here. So we have air at the given conditions entering the cooler, and some of the water is condensing and it's being delivered to a process at 510 meters cubed per minute. The problem didn't give a pressure, but I'm just going to assume it's 1 atmosphere because we're just taking air from the outside. I went ahead and drew and labeled it in terms of the total number of moles coming in, moles coming out, gave the mole fraction because we can use the definitions and saturation conditions to determine the mole fraction of water. And then I also labeled it with the moles of water coming out and then the mass of water coming out because this is one of the terms that the problem asks us to calculate. We're also going to assume, according to the problem statement, that the enthalpy of the water vapor is going to be that of the enthalpy of the saturated vapor at the given temperature. And then also it gives us a relationship for the enthalpy of dry air is 0.0291 times T minus 25, and this is going to be in terms of kilojoules per mole. These saturated enthalpy values for water from the steam tables in the back of the book gives us kilogram or kilojoules per kilogram. So we're going to need to convert that to moles because I'm just going to go ahead and end up solving this problem in terms of moles. So there's a variety of things that I'm going to need to do for this problem. The first thing is I'm going to use the definitions of relative humidity and the temperature to calculate these mole fractions, and I'm going to use the fact that because we have vapor in contact with a liquid, we know that the water in the stream coming out is going to be saturated, so I can use that to determine these mole fractions. I'm going to use ideal gas law to convert the flow rate coming out, the volumetric flow rate coming out, into a molar flow rate coming out. Then I'm going to do my mass and mole balances on the process. And then finally, I'm going to use the energy balance to calculate the amount of cooling required to do this process. All right, so let's go ahead. Let's start with the mole fraction. So from table B3, we can get the saturation pressure for water at 14 degrees C. And this is going to be for the conditions coming out. And this is 11.987 millimeters of mercury. So I can use this now. So the mole fraction of water coming out, it's just going to be 11.987 divided by 760. Because again, the partial pressure of water is equal to the saturation pressure of water because it's in vapor-liquid equilibrium. And this gives me a composition of 0.0158 mole water per mole. I'm going to use the relative humidity definition up here to determine the mole fraction in this stream. So we know that the saturation pressure of water at 38 degrees C from table B3, we can get this value, and it's 49.692. So therefore, the mole fraction of water in the inlet stream, it's going to be, because it's 97% relative humidity, it's going to be 97% of this value, 49692 divided by 760. And if I do this calculation right here, I'm going to get 0.0634 moles water per mole. Okay, now that I know these, I also know these just because we know that some of the compositions equal 1. So up here now I can use the ideal gas law to determine the number of moles in this stream. And because it's air at low pressure and normal temperature, it's very likely to be ideal gas law. So the number of moles in this stream right here, it's just so PV equals nRT, so PV over RT, and then the pressure, we're going to use 1 atmosphere, volumetric flow rate given is 510 meters cubed per minute. I'm going to use the R value that's in terms of liters, so I have 1,000 liters per meter cubed, over 0.08206 liter ATM over mole dot K. And then the temperature of this stream coming out is 14 degrees C, so that's going to be 287 K. And this number of moles in this stream will then be total coming out is going to be 21,655 liters, or sorry, we just converted that. So this is going to be moles per minute. All right, so this gives us this number of moles coming out. Now I can go ahead and also get the number of moles of N0 coming in by doing the air balance. So the total number of moles in this stream, the moles of air in this stream equals the moles of air in this stream. So from this balance right here, we're going to have the moles coming out as 21655 times the mole fraction of air in this stream. It's going to be, let's see, I look at this number right here, so 0.9842. And therefore this is going to equal the mole fraction in this stream, or it's going to be the total mole rate in this stream times the mole fraction. The mole fraction of dry air in this stream entering is just going to be 1 minus this value, so 0.9366. So then we can get this value N0 is going to be 22,755 moles per minute. I'm just carrying some extra numbers here. I mean, I have more significant figures than is needed, but I'm just carrying some numbers so that I can, keep my accuracy with the calculations. Okay, so what else do I need? Now I need to know the total moles of the liquid water coming out here. And so to get the moles of the liquid water coming out, I can just do a water balance on this process. So I have the moles of water here plus YW times N1 equals YW0 times N0, right? You can put those numbers in and work through that, and what you'll see is that the moles of the liquid coming out are going to be the moles of liquid coming out are 1101 moles water per minute. We can also, we don't need to write down the other moles. We can just use that for now. The problem asks us to calculate this right here. So to get this right here, I just have to use the molecular weight of water, and then also convert the units. And so if I do that, I will get a ml, the mass flow to the liquid water is going to be 19.8 kilograms per minute. All right, multiply this by 18 grams per mole and then divide it by 1,000. Okay, so what do we need to do now? So we've done our balances, we know the overall mole rates of everything. The next thing that we need to do is calculate our enthalpies for each component in each stream, and then put everything together for the mass balance, or for the energy balance. I'm going to give myself a little bit more space here, but I also don't want to lose the moles that I have written here. I think all of this stuff I can get rid of for now. Okay, so just to go back, so our energy balance for this process is going to be delta H equals Q, because there's no shaft work, no kinetic and potential energy changes. We're asked to calculate Q, which means that we should be able to calculate this delta H. So to get this delta H, right, this delta H is just going to be the sum of the enthalpies coming out minus the sum of the enthalpies coming in. So if we just look at the different species coming out, we have dry air in the vapor, we have water in the vapor, and then we also have, we keep this L here, moles water per minute. Then we also have water in the liquid, so those are all, we have to consider all of those enthalpies coming out. And then we have dry air coming in, and we have water coming in. So I'm going to need enthalpies for each one of those things. So let's go ahead and let's go ahead and calculate the enthalpy of dry air. So we can get the enthalpy of dry air. So dry air coming out, and we can get the enthalpy of dry air 0. So I'm going to use just the same subscripts designations as that I'm using for the species in the given stream, so that I can match those up later. So to get that of the dry air coming out, I just use this relationship right here. So I 0.0291 times T minus 25, and the temperature of this stream is 14 degrees C. So if I go ahead and do that, I'm going to get negative 0.3201 kilojoules per mole. Right, and this is a negative value, which is okay. We'll come back to that in a second. So the enthalpy of the dry air in this stream is going to be the same equation, 0.0291 times, now in this case, 38 minus 25, and that is going to give us 0.3783 kilojoules per mole. And these are going to be the enthalpies for the dry air in the two streams. This isn't accounting for water. What we can notice from this equation right here for the dry air is that the dry air is referenced to dry air at 25 degrees C. So in other words, the enthalpy of the dry air is set to be 0 at 25 degrees C, which makes that the reference state for that system. The steam tables in the back of the book uses a different reference state. They reference that of water at the triple point. And it's okay. It's okay that we have a different reference state for each one, because we're effectively calculating the change in enthalpy of the water. It's all versus the same reference state, and then also the changes in enthalpy of the dry air. For reactive processes, though, you have to have everything at the same reference state. So if there's no reaction, you can use different reference states for different species, and that is all fine. Okay, so what now? We need the enthalpy of the water coming out, we need the enthalpy of the water in the vapor entering, and then we need enthalpy of the water in stream 2. Okay, so in this case right here, this is going to be a vapor at 14 degrees C. Entering is a vapor at 38 degrees C, and then this is going to be a liquid at 14 degrees C. All right, so I'm going to get all these values from the tables. So we're assuming it's a saturated vapor, so we can go to table B5. If we do that for the 38, we'll look at this one first. We have, what's this one? 2570. And again, this is kilojoules per kilogram. So we need to take this and we need to multiply it by 18.02 grams per mole. And then take this and convert to kilograms per gram. I should write it this way, 1,000 grams. And if I do that, if I multiply and then I divide this through, I get 46.33 kilojoules per mole. I'll make it write that a little bit more clear for you. 46.33 kilojoules per mole. I'm going to do the same thing for 14 and the same thing for water. So this is 2572.8 from the table, 2527, 2527.8, 27.8. And then for the liquid, it's 58.8. And then if I go through, do that process, do the same sort of conversions for each one of those, I'm going to get 45.54 kilojoules per mole. And then down here we get 1.06 kilojoules per mole. So we have now the enthalpies for all of these different species. So these are the things coming out. This is coming out. This is coming out. These are the enthalpies of the species coming in. So now I just need to put all of that together, and we use this space right here. So again, we're going to have our Q. I'm going to separate this a little bit so I can, I'm going to write this a certain way. So Q is going to equal delta H. Okay, so that's, again, it's the sum of the moles times the H coming out minus the sum of the moles times delta H coming out. So let's just look at what these are. So coming out, we're going to have the moles of dry air. So the moles of dry air coming out are going to be YdA1 times N1 times H dry air 1. Plus, and I'm just going to write these down here, I'll show you why. The water coming out is going to be Y water 1 times N1 times H water 1. Plus, we also have water coming out in this stream, and that's just going to be NL times H, what do we call that? Water in stream 2. Which I call that L or 2, or whichever is fine. So that's that coming out in that stream. And now I have to subtract all of the species coming in. So I have the air coming in, so it's going to be composition times the total moles times the enthalpy. So minus YdA0 N0 times H dry air 0. And then also I have water in this stream, so I have minus YW0 N0 H water 0. Entering. So you can see, so I have the sum of what's coming in minus those things coming out. And I wrote it this way, just because I can show you that the other way you can kind of consider this is just, this right here is just the delta H. These two things up here at the top, this is just delta H of the dry air. And then these on the bottom this is delta H of the water. So the total delta H is going to be that of the air and that of the water. Or you can split up species like that. You can do the calculation like this. If you go ahead and now just plug in all of these numbers that we've already determined, you will get a cooling rate of, where did I put my numbers? You'll get a total cooling rate of, let's see, I'll write this down here. Q equals negative 6.5 times 10 to the 4 kilojoules per minute. But this book asks for tons of cooling, which says a ton of cooling is about 12,000 BTU. And if we do the unit conversions, we will get about 308 tons of cooling. This part right here, it's just units. So I'll let you go ahead and work through that, but I wanted to at least just give you numbers that you could work with and check to make sure that you got your things entered in correctly.